All right, hi everyone. Uh, Today I'm going to talk to you a little bit about spectrometers, and let me see if I can hide this a little bit here. I thought it would be interesting to walk through a couple of interesting things related to spectrometers and to talk a little bit about the use of derivatives and the use of smoothing in terms of spectral curves. This is something that can be applied to several different types of research, not only spectral research, but anything that has data that could be considered continuous and tends to have a lot of information associated with it. One of the things that I'm going to touch on very briefly today is the use of fiber optics. If you're ever interested in a book that just tells you a lot about the history and the story of fiber optics, I recommend this one by Jeff Heck, and it's called The City of Light, The Story of Fiber Optics. I came across this as a PhD student. I really enjoyed it, and I think it's going to be something that you'll find interesting as well. Let me start my video. I realize that I don't have my video running here. All right. With spectrometers, and I briefly covered this in one of the earlier lectures, but I found this great diagram from Ocean Optics that shows how an ocean optic spectrometer works. There shouldn't be any major surprises here, but let me walk through what's actually happening here. You have an inlet port here where the number 1 is, and that inlet port is usually attached to a fiber optic cable. So you see you have threads here, and you actually have a fiber optic cable that connects into it. And then the light comes in through the fiber optics cable, and it hits a mirror right at the back of the spectrometer. Now, one of the challenges you run into is that you don't have enough space right here to get enough dispersion to really disperse the light out onto all of your sensors to be able to pick up the quantity of light by wavelength. So it actually passes this light through 3 mirrors. There's one here, and one here. And in each of these steps, it disperses the light and increases the optical path so that the light can be dispersed more and more. And then you have a line of, it's called either a photodiode array or a CCD array, where you're essentially scattering the light out, and each of these individual sensors here is made out of silicon, and it detects the quantity of light that comes to it through this process. And so because the light's been dispersed, the shortest wavelengths are here on the top, the longest wavelengths are here on the bottom, and you're able to get a high resolution spectral image that looks kind of like this. This should look pretty familiar to you. This is something that I've shown you a lot of similar graphs before. This is the reflectance curve of a plant. This is the green right here. This is why we see plants as green. This is the blue. This is the red. And that was made using a StellarNet spectrometer, which looks very similar to an ocean optic spectrometer, works off of the same concepts as an ocean optic spectrometer, but it's just another brand. I've used Ocean Optics. I've been happy with them. I've used StellarNet. I've been happy with them. I also used an ASD spectrometer when I was at Utah State. These tend to be a lot higher dollar. They tend to be a very high quality spectrometer, but you're going to pay for it. The field specs, traditionally back when we purchased one, the cost was between about $50,000 and $70,000, depending on what you wanted to do. I think the cost now is over $100,000 for these instruments. But this dashed line right here, this dotted line represents the fiber optic cable. And then if you look at the tip of the fiber optic cable, this inlet here has what we call a field of view, meaning that the light that's coming into the fiber optic cable is only going to be captured from a relatively small area. Now you can change that area by putting on a lens, just like you would with a camera. You can put on something that's wide angle, you could put on something that's narrow. A lot of times when you're using just a bare fiber optic cable, the field of view is about 25 to 35 degrees for most of these fiber optic cables. And with ASD, they have this little gun-shaped thing right here, which just allows you to more accurately aim your fiber optic cable to take your measurement here. They also, let me see if I can find a multispectral camera real quick. These, if I can find one, are pretty interesting. They're very expensive. Most of the ones I'm seeing here are just the basic ones that you put on a UAV, and they're not overly expensive. Let's see. Let me try one more. I don't immediately see, this is probably going to be the most similar to what I'm thinking, but actually have cameras that can take images at any of a number of wavelengths, and those wavelengths are adjusted by essentially the equivalent of turning a dial like you would on a radio. And as you turn the dial, it picks up different wavelengths and it's able to take images at several wavelengths. So I've seen images where you can take an image at 400 nanometers, 401, 2, 3, 4, 5, all the way up to maybe 2000 nanometers. And you have images at each of those spots. Now, the challenge with those types of cameras is that you're only snapping one image at a time. And therefore, if your lighting conditions change at all while you're taking these pictures, that's going to affect the overall measurement. And so they don't tend to be used on aircraft or other aerial remote sensing platforms, but they're able to do a great job of measuring an entire scene reflectance or picture, as opposed to these are just going to give you one value that runs across the entire spectral range for any specific measurement here. We also had one of these when I was at Utah State that I used for my leaf area or my leaf level spectral measurements as well. So let's actually look at what some of these data would look like. I'm going to pull my Excel file over here if I can get it to actually, just a second. Okay, here's my Excel file. I actually pulled this from my PhD research from about 15 years ago. And these are the types of measurements that you get coming out of a spectrometer. If I graph this out, it's going to show me the typical leaf spectrum. No big shocks here. A lot of times we'll focus on this range and this range to get NDVI, and you can get an estimate of how big the plants are or how green the plants are. You can also do some more involved measurements, such as looking at, what's going on between individual narrow wave bands here. One of the ways that we do that is by doing derivative measurements. And you probably remember derivatives if you've had calculus. If you haven't had calculus, a lot of times we talk about it as if it's something amazing, but really all it is the change in y divided by the change in x. So, you go back to your geometry, and remember, slope is rise over run. Well, this is just rise over run on a very small scale. So what we're essentially measuring with our derivatives is just the instantaneous slope of this line at any given time. So just for the fun of it, escape here. Let me show you an example of what a derivative might look like. I'm going to take one of these over on this side. I'll tell you why in a minute. This is a typical derivative spectrum where anytime this number is high here, you've got a steep slope between one spot and another spot within your spectral graph. Anytime you've got a negative value, it means that you're sloping down. Anytime you have a zero value, it means it's more or less flat. This big peak right here corresponds with this spot right here where you have the maximum increase in reflectance between the visible and the near infrared. So you can use this to do a lot of really interesting things, such as, how high does this peak go? Can it shift from left to right? How high does this peak go? Does it shift from left to right? All of those things are measurable, and all of those things have had papers published on them. The answer is yes, you can actually shift the spectrum quite a bit based on your treatment. And so one of the problems that we tend to have, though, is if you zoom in on this graph, this is probably a little bit oversimplified. Let me just zoom in on this graph. When you take this measurement, you're going to take a reference measurement using a reflectance standard that's nearly 100% reflectance across the spectrum. And then you're going to point the same sensor at your plant and take another measurement. And then you're going to ratio those two things together. What you don't see is that you always have some level of high frequency noise going on. That's just, it's there because the sensor is always going to have some level of noise associated with it. If you're into electronics, a lot of times you start hearing about signal to noise ratio, and that essentially means that you have a high signal to noise ratio. It means that you have a lot of signal compared to the amount of noise that you do, and a high signal to noise ratio is a way of estimating how good your measurement's actually going to be. I'm just zooming in on this so that you can see all of these little dips and rises that we have in here. They weren't immediately evident when we were looking at the entire scan, but now when we're looking at it on an individual basis, they're pretty evident. So what ends up happening is when we do the first derivative, we end up getting a lot of what we call high frequency noise that shows up here. So you can still kind of see this general pattern that we have here, but you see a lot of stuff going on that is really due to those individual noise measurements and are completely independent of anything else. If we could completely eliminate the noise from both our standard and from our reflectance measurement, you wouldn't see that at all. So one of the methods that we use is spectral smoothing. There are a lot of different kinds of spectral smoothing. One that I've used for my work, let me hide this again real quick, is the Savitsky-Goulet smoothing. And so here's an example. Here's this noisy data here. You run a Savitsky-Goulet smoothing, and you can define over what range you want to run the smoothing, and you're able to essentially make this noise disappear. Then when you do your first derivative or second derivative measurements, it keeps everything clean and happy. Now, you also sacrifice something because you're potentially going to lose some information in addition to losing the noise. And so you have to be very careful to smooth things enough that you get rid of the noise, but not so much that you lose the information. So Here are some examples of different levels of smoothing. See, this is no smoothing. Come over to here. This is some smoothing. And this is, oops, more smoothing. Hopefully I selected these correctly here. So what you can see is that our two smoothed ones follow the same general pattern for the first derivative as our noisy data, but they don't have all the noise here. If I delete the noisy data, you see that these are nice and clean. They still have some peaks and dips, but you have to be careful. If you go super smoothed on it, you can completely flatten everything out and it disappears in this case. So take home summary from today. First of all, a spectrometer is an optical instrument that is used to measure reflectance by wavelength. You disperse light through a slit. You bounce it off some mirrors to increase the length over which you're able to disperse the light, and then you measure the amount of light on this photodiode array. You use a fiber optic cable to feed the light into the sensor. You could actually leave the cable off and measure directly from this, but you have to get the whole system really close to the plant in order to do so. There are different types of spectrometers out there. I showed you three: Ocean Optics, StellarNet, ASD. Sometimes we'll have, add-ons that allow us to do individual leaves. If you want to learn more about fiber optic cables, I recommend this book. There are cameras that can measure individual wavelengths and take a picture at an individual wavelength. And then finally, you can use smoothing, not only with spectral data, but with any high frequency data in order to smooth it out and to remove some of the noise. I hope you've enjoyed this lecture, and I look forward to seeing you next week.